All right, so today we're going to talk about the exterior product, or the wedge product, or why the cross product is evil and what to do about it. So, first off, let's start with some review of the cross product. So, we talk about the cross product because we want a way to describe planes and a way to describe rotation. And so we look at this, we have this operation, binary operation in R3, that gives us, given two vectors, a vector that's normal to the sort of plane bounded by them. So it's perpendicular to u and v, and the magnitude of this vector is the area of that parallelogram. Some other properties is that the cross product is bilinear and alternating, so it preserves all sorts of scalar multiplication and addition. And the cross product of a vector with itself is 0, which also implies that it's anti-commutative. So if you flip the arguments, then you get the negative. And the other axioms on top of that for the cross product are this sort of cycle that I cross j is I hat cross j hat is k hat, j hat cross k hat is I hat, and k hat cross I hat is j hat. So this is sort of based on our choice of orientation. And so these can characterize the cross product. And from here you can compute the general formula, or if you insist, you can do this weird little determinant, formal determinant with the unit vectors and the components. And we also have this right-hand rule. So when we're doing a cross product of two vectors, to figure out the direction that the cross product will be in, we can look at our hand to see what that will be. And as a result, the vector, the quote-unquote vector we get out, isn't necessarily fully normal, fully like other vectors, in that if we do a certain transformation that flips our orientation around, like looking at a mirror or something, then suddenly our cross product flips directions. So in settings where that's relevant, sometimes we call the cross product a pseudo-vector. Okay, so since we're here to talk about better options, let's talk about some complaints with the cross product. So first off, some somewhat major problems. So one question we might have looking at this operation is, well, we have this operation in R3. Do we have a generalization, some sort of alternative for n dimensions? And the answer is no. We have a cross product in R3, and we also kind of have a cross product in R7, which is neither here nor there. But yeah. So this is kind of strange because, if we have this tool to talk about planes and rotation, and well, we have planes and rotation in dimensions, so it's sort of this strange arbitrary seeming choice of R3 for the cross product to live in. Another problem is this thing about the right-hand rule, which is that, for our general operation, it's apparently dependent on this, again, seemingly arbitrary choice of orientation, and in certain contexts, that could even get sort of messy if we're doing transformations that change orientation, when normally we expect those to leave vectors behaving as normal. These quote-unquote pseudo-vectors sometimes mess with that. So that's another kind of concern, is that this is another sort of arbitrary choice about the right hand, like it could have been the left hand, and it's also not even invariant under all of the transformations we expect it to be invariant under. So yeah, our big problems are that the cross product has these arbitrary choices, and that makes it a little bit clunkier to work with and think about. So while we're here, we can talk about other concerns that we have, other little red flags that aren't necessarily problems per se, aren't necessarily glaring problems, but they sort of indicate that something's off, and they might even give us hints as to what we might prefer instead. So one question is, what is U cross V cross W? We already have this formula. We can compute the cross product of two vectors. So maybe you would try like plugging this formula in to try and get the cross product of these three vectors, but this is actually a trick question because this is not a clear expression because the cross product is not associative. So depending on where you put your parentheses, so in which order you plugged your formula in and which order you computed these terms, you would actually get a different answer. And in fact, we have the cross product satisfies what's called the Jacobi identity, so we can know that it's actually this is what the difference would be, depending on which order you did your computations in. So this sucks because we normally like our operations to be associative, especially if we're calling them like multiplications. Like products kind of should be associative. It's very strange and like a sort of concerning way that we can't do this computation independent of like the order we put our parentheses because um, the sort of notion of like, oh, getting a vector that's normal to the two other vectors doesn't really seem like it should be conducive to that. So that's a little suspicious. We also have that weird formal determinant, which like isn't necessarily evil because like it's just a computation trick and it's fine to do weird things like just to make remembering computations easier, but it's a little bit suspicious, um, especially because we're talking about a determinant when we're really trying to compute like a vector, while determinants, in general, when we're talking about like linear transformations, determinants really talk about how we transform areas or hyperareas in however many dimensions. Um, and so that's a little interesting that we sort of do this operation that seems to be more related to areas when we're getting a vector. And actually, on the same vein, um, the one-dimensional length, like the length of our one-dimensional cross product vector, is equal to the area of a two-dimensional parallelogram, which is again, it's not necessarily like bad, but it's kind of suspicious that like, is this really the best way to be representing and modeling what we're trying to do? Because like if you think about like for example like the units on that number is weird, right? Because for some reason this one-dimensional object, taking this measurement on a one-dimensional object, is giving us a measurement for a two-dimensional object. It's just a little strange. So anyways, really in general it looks like, so we already know we're trying to talk about planes, um, but let's do a quick interlude and see if, given all of these ideas, we can come up with some other way to sort of do what we're trying to do here. So we're trying to describe planes in rotation. And the cross product takes advantage of this notion that, well, if you have a plane, um, or if you have a rotating system, in both cases you have this associated vector. You have the normal vector to your plane, and you have the axis of your rotation. Seems okay, but as it turns out, if you think about it, rotation isn't always about an axis. And in fact, planes don't always have normal vectors, at least if we look intrinsically. And so, when not? Well, in R2. Because in two dimensions, we don't have that space, we don't have a third axis for that extra normal vector or for that axis of rotation. So rotation just happens in R2. And the plane just is R2, right? There's no other axis. So the question then becomes, what should we be talking about for, say, rotation if axes aren't covering all of our cases? Well, we see that in this Cartesian plane, at least, we just have rotation without needing it to be about an axis. So maybe what we should be thinking about is a plane in general, because even in the general case, Rotation, although you could say it happens about an axis, even more generally, rotation just happens in a plane. And we see that here where there's no room for an axis unless we um, want to extend to a third dimension, which we don't really want to do if we don't have to, right? So really we can just consider this rotation to be happening in a plane. And even simpler, planes are planes. We don't necessarily need to associate this other object with them because rotation happens in a plane, planes happen in a plane, so they have another object in common, planes themselves. So really it looks like the cross product is okay. So let's see what we can do now that we've done this brief interlude about where we've come to the conclusion that sort of we really do want to be talking about planes because planes have all the information we want, and it feels like right now we're kind of grasping at that idea with the cross product without fully reaching it because we're still producing a vector. So yeah, our tool for talking about this is a little messed up. And it's kind of because it's trying to describe a plane with a vector, this 2D object with a 1D object. So maybe we should just talk about planes. And what we're going to do here now is talk about another idea called a bivector. And so this is going to be, so the idea here is with a vector space, we have these notions of different dimensionality in our objects. So we have scalars, which are like zero-dimensional, just like points on our number line, right? And we have vectors, which are like one-dimensional, sort of oriented line segments. And then the natural step then is we have bivectors, which are two-dimensional, oriented plane segments, or oriented areas. So where a vector is an oriented magnitude, an oriented length, a bivector is an oriented area. And so we get a vector space of these with, so if we have, say, 3 basis vectors in R3, we have 3 choose 2 basis planes. This is 3 choose 2 because our basis planes are going to be however many ways you can pick 2 basis vectors and take the plane that they sort of span. So like you can decide which 3 basis planes you have, but in R3 it'll always be 3. So for example, you could pick the XY plane, the YZ plane, and the XZ plane. Yeah, and so technically in general, this is what's called the second exterior power of V is this bivector space, and we can generalize this to arbitrary K talking about K-dimensional objects in our space. So we can be talking about zero-dimensional scalars, one-dimensional vectors, so like line segments, two-dimensional bivectors, so like plane segments, and then like volume segments, and etc. So now we have this mechanism to talk about planes, which is what we were trying to do at the beginning. Seems like what we've been trying to do with the cross product this whole time. So now the question becomes, how do we produce bivectors? Like, how do we actually get these objects so that we can work with them? And the answer here is the exterior product. So, the exterior product actually is a little bit more general than how I'm presenting it right here. But here we can think of it like taking in 2 vectors and producing 1 bivector. It's also called the wedge product because we denote it with this wedge. So as we would sort of hope, U wedge V is this oriented area between U and V. And this is, by all accounts, the object that the cross product was trying to get at, right? This is what the cross product was sort of aiming for, but really, like, this is actually the object we want. We really care about this plane, because the plane, if we're talking about planes, yeah, we want the plane, and if we're talking about rotation, we can talk about rotation happening in a plane. So now those basis planes I was talking about before are to take the plane spanned by those 2 basis vectors for some notion of span. we just wedge them together. So this operation kind of looks like the cross product, right? Which we would sort of expect. We're kind of hoping, since it's supposed to be doing the same thing, at least the good parts of the cross product should be preserved here. And we get that. So, for example, the area, the norm of this vector, the magnitude of this vector, is that same norm u, norm v, sine theta area of this parallelogram, which is perfect. It's what we wanted. And now it's no longer as dubious to say so, because we're taking the magnitude of a two-dimensional object and we're getting the area of a two-dimensional object. Although that's a geometric, sort of geometric dimension here, because we're talking about areas, not necessarily the dimension of the vector space. And we get, so yeah, anyways, we get a lot of those properties of the cross product as well. So it's bilinear and it's alternating. And with the cross product, we were able to characterize it precisely with these two properties and those choices for the cross products of the basis vectors. Here we almost get that, but it's in a little bit of a different way, where we have this universal property that tells us that really this bivector space and the wedge product is the sort of the quote-unquote universal setting where this holds. So it's kind of the most general world in which you have these properties. So any other setup where you have this space that kind of looks like the bivector space that has a bilinear alternating product, it sort of does so through this space in a precise sense. Yeah, so as I was saying, what the cross product does, that extra property that we had on the cross product, that I cross j equals k and so on, that is basically based on the orientation, that right-handed orientation chosen. The cross product picks a basis for the bivector space. It decides which components, which basis planes to project your oriented area onto to get your components. And then it casts those components from being projected areas on a basis plane to being length on a basis vector. So, and if we pick that same basis where we say j wedge k corresponds to what would be I hat, and k hat wedge I hat corresponds to what would be j hat, and so on, we get the same components. So it's all the same computation here. This is in some ways, this is in large part a change in perspective that just makes the the things that the cross product is trying to do more explicit and a little bit more intuitive, I feel. And yeah, you might notice that formal determinant would still work if you're depending on your choice of bivector basis. And yeah, it's still a little weird, but it is a calculation trick and it's a good mnemonic or whatever. And it actually, we can shed a little bit more light on what's happening by recognizing that as we generally define the determinant, it is actually doing a multilinear alternating map. And that kind of corresponds to how the determinant talks about hypervolumes, is because the determinant is working with a multilinear alternating map, and by the universal property of the exterior power, we see that is going to happen through these wedge product related setups. So yeah, so the wedge product is a lot like the cross product, but it's better. So for one, it works in arbitrary vector spaces. We're no longer stuck in R3 for some reason. Oh, and that weird reason, as it turns out, was that the cross product is able to sort of typecast the components of a bivector into components of a vector, because in R3, the dimension of the bivector space, 3, is the same as the dimension of the vector space, 3. This is because, yeah, it's because 3 choose 2 equals 3. So we're able to sort of we're able to confuse bivectors and vectors, and sort of treat them all as vectors when really, just by virtue, or I guess kind of the lack thereof, of the fact that they are the same dimensions. So this lets us kind of forget the distinction between them. But yeah, the wedge product works in arbitrary vector spaces, Euclidean spaces, whatever, tangent spaces of manifolds, which is important, etc. It's independent of orientation. The cross product pins you down to one choice of orientation, and that forces you to use the right hand rule. It leaves you with, in those certain contexts, it leaves you with a pseudo vector, so you don't always transform the way you'd like, because the cross product like intrinsically encodes this unnatural arbitrary choice of basis. Unnatural in that it doesn't necessarily play well with of the transformations we'd like it to be compatible with, because it makes this arbitrary choice every time. The wedge product is associative. That's good news. Thank goodness. Now, technically, to talk about associativity here, since I'm technically wedging a bivector and a vector here, so we would really be looking at the more general wedge product that takes in a k vector and a p vector and gives you a k plus p vector. So really, we're looking at like a tri-vector here that's an oriented volume, but it doesn't really matter. The point is that it's associative, while the cross product wasn't. And yeah, so the important thing here is that we're no longer sort of grasping at this idea of a plane through only the notion of a vector, right? Now that we actually have this language of k vectors, or bivectors specifically here, we can use this wedge product, this exterior product, to talk directly about planes themselves without having to sort of take advantage of coincidences that let us turn this data into that of a vector, that of a confusing and sort of dubious vector, and instead it lets us actually talk about the plane itself. So yeah, that's the exterior product. That's why the cross product is evil, and that's what we should be doing instead.